Let's start our session on trig identities on looking at where they come from. So where do we get them from? It's a unit triangle. So unit triangle is just a really funky triangle where the hypotenuse, triangle not a flag shall we say, is 1. So we have a right angle triangle if we're dealing with a hypotenuse. And let us say that the bottom of this triangle is x and the side is y. Now we can build some really fun things from here. If we think in terms of SOHCAHTOA, sine, cos, and tan, that wonderful little friend of ours, we need to add in one more thing for our triangle. We need, of course, an angle that we're considering. As usual, we're going to call our angles theta. Sometimes when we're working in trig, we actually come across x quite a lot as well, but x is a side in this one, so our angle is our standard theta. So let's have a think a little bit about what sine of theta would be. Sine of theta would be opposite over hypotenuse. So y over 1. But that's exactly the same as y. What would cos theta be? Cos theta would be adjacent over hypotenuse. So x over 1. And that is the same, of course, as x. What would tan theta be? Tan theta would be opposite over adjacent. So y over x. But we've just said that y is exactly the same thing as sine theta. And x is exactly the same thing as cos theta. So now we have a wonderful relationship, avoiding x and y completely, that tells us tan theta equals sine theta over cos theta. And that is the first of your AS identities. And I remember it, which way around? Tan is sine over cos. Okay, so tan theta is sine theta over cos theta. Tan x is sine x over cos x. Lovely little relationship. If we look, okay, right angle triangles, we've used SOHCAHTOA. The other one would be, of course, Pythagoras. Now, Pythagoras would tell us that 1 squared equals x squared plus y squared. Well, 1 squared is 1. And x and y? Well, x is cos squared theta and y is sine theta. So y squared is sine squared theta. So just a little note, okay? Cos squared theta is cos theta times cos theta, okay? But we write it with the squared on the cos so that we don't get confused with what's going on with the angle. So whenever you see cos squared, it means cos theta times cos theta. If you see sine squared, it means sine theta times sine theta. And funnily enough, again, we've gotten rid of both x and y. And we have a relationship involving a cos and a sine and a 1. Now, 1 is such a lovely number to work with. So we have another beautiful relationship of 1 equals cos squared theta plus sine squared theta. So there's a few things to note here. These are your two identities. Now, an identity means that the things are exactly the same. Okay, so 2 times x and 2x are exactly the same. You wouldn't have even the second thought about interchanging 2 times x and 2x because they mean exactly the same thing. And it's the same with these. If you have tan theta and instead of writing tan, you write sine over cos, it is exactly the same. And that's why it's called an identity, and that's why it has this special triple equal sign. Okay. If you have 1, you can write cos squared plus sine squared. It's exactly the same. Okay. This one, though, we often use in a rearrangement because we can say that cos squared theta is the same as 1 minus sine squared theta, or we can say sine squared theta equals 1 minus cos squared theta. And these are identities. So again, we would actually have our triple equals. So this one, the cos squared and sine squared, we often rearrange so that we can either substitute for cos squared or substitute for sine squared. The tan one, we don't tend to rearrange it. Tan is sine over cos. But remember here, you've got only one term on either side. So tan squared would be sine squared over cos squared. So bear that one in mind when it comes to tan. You can square, you can cube, you can do what you like. You can flip it over. 1 over tan theta is cos over sine theta because only one term on each side. So why do you need to be familiar with the gymnastics of these? It's because of what we're going to do with them. What we use identities to is to simplify things. Remember, when we want to solve an equation, we need to have only one function present. So in order to get one function, sometimes our trig equations don't have one function to start with, and we've got to manipulate them so that we do have one function so that we can solve an equation. So our aim of the game when it comes to trig identities is to replace and to simplify. So obviously, if you've got a sine theta over a cos theta, you could replace it with a tan theta. Hey, if you've got a 1, you could replace it with a cos squared plus sine squared. Well, if you've got a cos squared plus sine squared, you could replace it with a 1. If you've got a cos squared, you could replace it with a 1 minus sine squared. If you've got a sine squared, you could replace it with a 1 minus cos squared. So there's all these different possibilities that you're going to work with, and you've got to keep them in your brain. So you've got to be really familiar with these identities so that when you sort of see things in a question, it's like, I know what's going to go there. I know what I need here, so that you can then work with them. So a few other things to bear in mind. Algebra is really important. Algebra and trig identities. Now we're talking back to basics here. Okay, so what we are doing is we often have a something is the same as something else. Prove it. Right? And this side will be horribly complex and this side will be wonderfully simple. So we're going to take our complex side and we're going to manipulate it and make it into simple. So we are not solving equations here. We are not moving things from one side to the other. It is very simply, very straightforward, algebraic manipulation only. And our general approach is manipulate that complex left-hand side until it looks like the right-hand side. Manipulate, not moving, not adding and subtracting, not multiplying, not dividing, just manipulating. So we've got our identities which we can replace. Obviously, that is one of our manipulations. But there's a few other things we keep in mind. First one would be converting fractions. Can you get your fractions to a common denominator so that you can add or subtract them? Right? It's a key skill because often we have fractions involved here. Often we're going between one term and two terms or two terms to one term. So how are we converting our fractions? Of course, if we're going to be converting them, readiness for addition and subtraction, we have to be able to do that fraction algebra. So I've been squealing in your ears for a while that fractions are your friend, and now I'm being point proven. There is no way you can do this in decimals, okay? It is algebraic fractions that you have to work with in order to be doing trig functions in fractions. We're not using calculators at any part of this identity work. It's all brain work. Right, third one, factorization. You have to be able to see it. You have to be able to do it. You have to be able to know when it's going to come and see ahead a few steps. And you have to not miss it. Okay? Linked to that factorization is a particularly special factorization that often comes up in trig identities. I noted it many, many moons ago. Difference between two squares. So when we talked about quadratic factorization, this came up, and I said, you know what? This is part of quadratic factorization. It's something you need to be able to do, something you need to be able to recognize, so that you see it and you click. You're not sitting thinking, what must I do with this? Okay, so difference between two squares. This is a key skill that's going to come up now. So the thing about these is that, okay, right, we've got these identities. We've got tan theta is sine theta over cos theta. We've got cos squared theta plus sine squared theta is 1. And we've got this idea of algebraic skills that we need to be sort of on top of, but there's no real way around identities other than doing them. So I've got a collection of identities here that we're going to work through so that you can see how these things start to pull in and you start to use these different skills. Our first one. 1 over, whoopsie, it helps if you write out the question correctly as well. 1 over 1 plus sine theta plus 1 over 1 minus sine theta is the same as 2 over cos squared theta. So this is just a very straightforward prove that this complex mess equals this beautifully simple side. So remember, we're going to ignore the simple side. We write it down so that we can got it in our head of where we're aiming for, but we're not going to work with it. We're going to work only with this left-hand side. And in a situation like this, I've got a straightforward starting point. Okay, tan is not involved. We're not worried about him. So we're working now with sine and cos. What we've got on the left-hand side is 2 terms. What we've got on the right-hand side is only 1. So we need to combine this into 1 term on the left-hand side. How do we do that? Common denominator and add our fractions. So our common denominator would be 1 plus sine, 1 minus sine. So we're going to have to multiply accordingly. So if we multiply top and bottom by 1 minus sine, we're going to get 1 minus sine theta, then plus 1, and on this one we'll be multiplying by 1 plus sine theta, top and bottom, so 1 plus sine theta, all over 1 plus sine theta, 1 minus sine theta. Now you stop and you think of it. Okay, so if you want to do that addition in 2 steps, make your one fraction, make your other fraction, do your addition, go for it, but you should be at a stage where algebraically you understand this conversion to a common denominator and can do the addition. Be careful if you have a subtraction. That is why I keep this 1, even though it's a 1. Okay, if it was a 2, if it was a minus 3, if it was a plus 10, if it was a minus cos, I'm going to keep it there in the idea that then I'm making sure that I'm protecting the sign in the middle, this plus sign rather than this sine of a sine theta. Okay, so on the top we have 1 minus sine theta plus 1 plus sine theta. On the bottom we have 1 plus sine theta, 1 minus sine theta. Now that should be ringing a bell, because we have a 1 and a 1, a sine and a sine, a plus and a minus. We have difference between 2 squares. So if we expand that, we have 1 minus sine squared theta. Maybe some bells are starting to ring now. So why did I show all of this on the top? It's because this is a proof. Okay? When we're doing a proof, we need to show every single step of our work in. That is what our examiner is looking for. So we don't want to be skipping things. We don't want to be merging steps. We want to be clear. So 1 plus 1 is 2. Minus sine theta plus sine theta is 0. And what is 1 minus sine squared? remember we had tan is sine over cos, and we had sine squared plus cos squared is 1. So cos squared is 1 minus sine squared. The 1 minus sine squared is what we were looking for, because that is then cos squared theta. So we have one piece of the identity. Next step, straight to replace it, cos squared. And magically enough, it's wonderful with identities because you always know when you're at the end, and you always know, did I get the right answer? 2 over cos squared theta, we have shown. We have ended up at that simple right-hand side. So let's do another one. There is another slightly different format that we get, and that is something like sine theta plus cos theta equals 2 sine theta minus cos theta. Okay, and they want us not here to do left side is the same as right side, but they want us to write this as an equation in tan theta. So that means we need to work through these identities again, and we need to think, okay, how are we going to get from sines and coses to tans? Okay, well, tan is, remember, it can help if you write them down to start with. Tan is sine over cos. So that might be where we're focusing on. If we divide through by cos, we would convert to sines. So let's get rid of this bracket to start with. So sine theta plus cos theta equals 2 sine theta minus 2 cos theta. Okay, well, now we can see we've got a whole lot of like terms. So let's simplify things a bit. So this would be 0 equals 2 sine theta minus sine theta would give us sine theta minus 2 cos theta minus cos theta minus 3 cos theta. Now, the thing is that we want to go to tan. So in order to get tan, we need a sine over cos. So we can divide through by cos. Cos theta. Cos theta. 0 divided by cos theta, of course, is 0. Right. Now, the question that comes up here is, how can I divide by cos theta? Because it's like dividing by an x, isn't it? And I can't divide by an x. The thing here is that when you're dividing by this cos theta, it's not disappearing. Because the cos theta stays, yes, it cancels, right? So you're going to get a 0 equals, and you're going to get a minus 3, because cos theta over cos theta is 1. The cos theta is still part of your equation because it's incorporated here. Sine theta over cos theta is tan theta. It's a very different story to if you have one of those quadratics and you divide by x and you lose the solution. Here, our cos theta is staying within. So equation in tan theta equals 3. So similar sort of approach, we're using our identities, but it's not the same as proving left equals right. So now we've done a few things. Let's try another one. Let's look at tan x plus 1 over tan x is the same as 1 over sine x cos x. So here it's a proof. Prove that the left-hand side is the same as the right-hand side. So, of course, we started only with the left-hand side. We're going to manipulate it algebraically until we get the right-hand side. So we've got two things to think of. Remember we said when there are 2 items on the left side and 1 item on the right side, then we need to combine fractions and put things together. The other story we've got here is we've got tan on the left and sine and cos on the right. So in this case, the first thing we're going to do is make these tans into sines and coses. So tan is sine over cos, but sine x over cos x. Plus 1 over tan x is just the reciprocal, right? So cos x over sine x. And there we stop. No equals because we're doing algebraic manipulation. Remember that equals has a meaning, it has a functionality. So we're not writing equals anywhere on here, we're just stepping through algebraic manipulations. Okay, so 2 different denominators. Again, we have to do this whole common denominator story. So we would have sine x on top, on the left, plus cos x over, common denominator is cos x sine x. Now what have we got on top? We have got sine squared x plus cos squared x. And on the bottom, well, cos x sine x is multiplication. It's the same as sine x cos x. So we've got the bottom of our end story. Now we have to just think about the top. And remember, we had those 2 identities. We had tan is sine over cos. And we had sine squared plus cos squared is 1. And what have we got on the top of our fraction? Isn't it wonderful? We've got sine squared x plus cos squared x, which is 1. So we have 1 over sine x cos x. We are matching our beautiful right-hand side. We have shown that our identity is correct. And I love these things because they're just so beautifully logical. Sometimes they'll keep you thinking. Sometimes you'll have a few pages of scribbles before you get to them if you make a mistake or if you go in the wrong direction. But the thing about identities is that lovely flow of step by step and thinking carefully, then you always get to the right answer, and it's wonderful. Okay, I think we've got time for one more. So let's have a look at something else. Okay, so one more. We have 1 plus cos theta over sine theta plus sine theta over 1 plus cos theta. This is apparently the same as 2 over sine theta. Wowzers. Okay, so let's get there. Now, we need a 2 on top, we need a sine theta on the bottom. We've got causes and sines, okay? We can work with that because, of course, cos squared could be sine squared. There's things going on there. We don't have tan to worry about. We have 2 terms and 1 term, so we need to do that fraction thing again. So on top, we would have 1 plus cos theta, 1 plus cos theta. Note how that original 1 plus cos theta went in brackets because it's the whole of that top times the whole of the bottom of the other fraction. Okay, plus sine theta, sine theta. Here we're not so worried about that sine theta going in a bracket because it's only 1 term. When you have more than 1 term, bracket it, keep it safe. Common denominator, sine theta, 1 plus cos theta. I forgot to change colors for this one. Obviously, very excited about doing identities. Okay, now, on the top, we want to get to a 2. So we're going to need to open some brackets and think a bit. But on the bottom, we want sine theta. So we don't want to open this bracket. We want to leave that sine theta. We love him there. So we don't want to open up this 1 plus cos theta. Even then, maybe we can get rid of him later. So on the top, we have 1 plus cos theta, so 2 cos theta plus cos squared theta. And then here we have plus sine squared theta over sine theta, 1 plus cos theta. Now, can you see it? Remember, we've got cos squared plus sine squared is 1. So on top, we actually have 1 plus 2 cos theta plus 1 over sine theta, 1 plus cos theta. Well, obviously 1 plus 1 is 2. So our next step is 2 plus 2 cos theta over sine theta 1 plus cos theta. Remember I said that we need to be aware of our factorization? There he is. Okay, so we're going to continue up here because we've run out of space. You would work down all the way. So 2, 1 plus cos theta, do you see the magic about to happen? Over sine theta, 1 plus cos theta. And now we have multiplication. We have multiplication. We can cancel. We do not draw lines to show that cancelling because we don't want to disrupt the showing of our factorization. But we just write on our next line 2 over sine theta because our examiner can see what we've done with the cancellation. We don't have to draw the lines through it. Okay? We have ended up exactly where we want it to be. We have shown that all that nonsense on the left-hand side is exactly the same as 2 over sine theta, which is so much easier to work with if we're using it in solving an equation. So if we had an equation with that horrible left-hand side equals 3, then we could put in our 2 sine theta instead and then solve that equation much more happily. So identities are a wonderful way of simplifying life when it comes to trig, to get complex things into formats that we can actually then work with to solve equations. But it is really, really, really important that you learn your identities and you've got a good grasp of those algebraic techniques so that you can start to combine them as you work through these. Because you don't want to be sitting for half an hour with a 2-mark question. Okay, you want to have a good grasp of where you're going and what you need to do. And the more you do, the better. And the more you do, the more patterns you'll see. And the more they will start to make sense.